An optimized algorithm to select the most appropriate gate type for a given railway level crossing in Sri Lanka. This is a project carried out by Pungdi Fernando, Anujabulat Sinhala, Dinitha De Silva of Intake 34, Department of Electrical, Electronic and Telecommunication Engineering. Rail services in Sri Lanka were commended by Britishers in 1864. Thereafter, the train tracks were extended to Kandy and to Central Hills to transport tea. With the expansion of road network, the need of level crossing became prominent. There are 1,300 railway crossings in the country. The roads were constructed in parallel with the rail line. In order to facilitate, links of the level crossings were needed to be constructed in short intervals. Earlier, level crossings had flagmen who, on approach of a train, waved the red flag or lantern to stop all the traffic. Manual or auto barricades were introduced later. The railway network consists of 9 railway lines, which are Main Line, Matale Line, Puttalama Line, Coastal Line, Kalanivari Line, Northern Line, Mana Line, Trincomalee Line and Batiklo Line. The operations of Sri Lankan Railway have been distributed to 3 divisions, namely Colombo, Navalapitiya and Anuradhapura. This project is carried out to prevent or rather minimize train vehicle or human collision by focusing mainly on railway level crossing based on pedestrian or vehicle well-being. The main research problem that we identified was, in the current railway system, there is no specific criteria to determine what is the best protection method for a level crossing. And also, Sri Lankan Railway spends about 25,000 rupees per month as wages for each barrier protected level crossings. In addition, trains and vehicles or trains and pedestrian collisions are higher, and also failures in level crossings result in road traffic congestion. The objectives of this project: identifying shortcomings of current railway signalling and protection system. What can be done to overcome the problems? Statistical and mathematical analysis. Selecting the parameters that has effect on gate type selection and model development. Before carrying out this project, a survey was done on this project. From the survey conducted by the group, we found that installing barriers cost around 1.2 million rupees. As it is very costly, Sri Lanka Railway does not install barriers to all the level crossings. And also, Sri Lanka Railway doesn't have a proper algorithm to decide whether to use bell and light or a barricade. The factors they consider are complaints from people living near the level crossings, nature of the road, whether it is a main bus route, or the traffic congestion of the road. Even though they install a bell and light system, it is not completely safe because the bell and light system breaks down in certain areas due to rain and other environmental factors. In the current system, if the relay is not working, the bell and light is working continuously until it is fixed. When the bell and light is not working continuously, people don't care. There is no way to know whether the bell and light doesn't work. Train and vehicle collision at level crossing amount to total of 31 deaths until May in 2019. This project was carried out in different steps. These steps can be shown as identifying the factors for the algorithm, data visualization and finding the correlation factors, data validation, and developing the solution model using the correlated factors. The factors we considered to build up the algorithm were train vehicle unit, type of protection, availability of an alarm system or a signaling system, number of accidents, visibility, bend, vegetation, gate mechanism, number of tracks, and construction in the level crossing. From these factors, visibility, number of accidents, train vehicle unit, bend, availability of a signaling system, availability of an alarm system, protection method, has strong correlation with the response variables. Hence, these variables have been chosen as a predictor variables for the algorithm. This algorithm is developed using regression tree model. This is a graphical representation of the model which has a leaf size of 36. The above model shows the increment of the parameter. Minimum leaf size was set to 93 as per minimum error and best point of hyperparameter stable observations which result in a coarse tree and a simpler model. Less computational time and better model which was proved from the obtained R matrix parameters. This table is generated to identify predicted results according to original results. As you can see, the model has suggested a bell and light system from some of the unprotected railway crossings considering the before mentioned factors. When optimizing the tree model further, best performance was observed at minimum leaf size of 94 with root mean square error value equals to 0.37 and R squared value equals to 0.74. It is observed there is a significant improvement in unprotected railway level crossings turned into bell and light protections, which is a plus that will result in a smaller number of accidents, and also there is a decrease in the percentage of barrier protection, where the model predict the existing barriers should be bell and light. With more training data, model can be further optimized to get a higher accurate decision. That's the end of this presentation. Thank you.